In this session, we want to cover two rules that govern data. Wow. So it's like they are very predictive and they need very little to be so predictive. So that's kind of nice to know without spending a lot of money, time, effort, calculations, whatever. We can straight away tell the mass behavior of the data. That's nice. And why is that possible? Thanks to these two rules. Now, they are not totally free lunch, as in, oh, you don't have to do work and then you can predict a lot with quite accurate outcome. That would be nice, but that's not possible. So there's no free lunch, sorry. But these two rules are still incredibly useful to know, because when we don't have a lot of resources and we are interested to at least be able to have some initial estimates of the population of data, then this will be nice. Applying these rules will be great. So the empirical rule and the Chebyshev's rule. The empirical rule first. It has got to do a lot with the bell curve, the normal distribution. And if we are able to say the income, let's say you arrive in a particular country first time because you are doing overseas studies, or you are posted overseas to work there and you are so excited you are reaching that country for the first time. So how can you apply this rule, right? This empirical rule. So empirical rule says if the population mean is mu and the standard deviation is sigma, then within one sigma to the left and right of the population mean, the whole set of data will be amounting to about 68.26%, means roughly 70% of the data will be in this range. So you arrive at that country, let's say you're interested in, roughly how much do these people earn, right? Okay, so suppose from some national data barrier, you manage to get the average salary, average income of that country, and okay, so some estimation says the standard deviation is this much. So let's say 100,000 and 10,000. Okay, so 100,000, 10,000, then you can, if you apply empirical rule, you can conclude immediately that, wow, about 70%, 68.26% of the entire population of working people, their income is actually from 90,000 to 110,000. Wow, something like that. You can conclude right away, approximately, but not too far wrong. Okay, and the reason why we have the 0.26% and all that actually is just based on the standard normal distribution, where mu is 0 and SD is 1. So you can just do that calculation yourself. You'll find that the area contained from -1 to 1, z equals to -1 to z equals to 1, the area will be 68.26%. That's assuming that the income or the data set follows normal distributions precisely, completely. But no data set in real life follows normal distributions perfectly. Okay, not at every point. But then a lot are well approximated by normal distribution. So well, the empirical rule tells us this, right? So 68.26% will be from mu minus sigma to mu plus sigma. So in my income example, you don't know the country at all. You haven't really buried yourself in the library to study everything about it. But straight away, just with two numbers, average income 100,000, standard deviation 10,000. And you heard that the income distribution is roughly like a bell curve. Okay, then straight away you conclude about 70% of people earn between 90,000 to 110,000. Additionally, you can say 95% of the people earn between 80,000 to 120,000. And up to almost everybody, almost 100% of the people earn between 70,000 to $130,000 per year. Okay, so it is pretty predictive. You haven't done any research, you haven't asked any person, just with a few numbers, two numbers, mu, sigma, and the knowledge that it looks a bit like a bell curve, that's all. So pretty nice, right? So that's pretty predictive. But again, there's no free lunch. You have to satisfy two um, conditions, right? So the data set has to be roughly moon shaped. That means it's kind of a lump, all right? So it's roughly moon shaped and roughly symmetrical about the mean, of course. Now, what do you mean by roughly moon shaped? So um, you can have symmetrical data sets but not moon shape. So that's roughly symmetrical. Of course, no natural data will be exactly symmetrical. So long as they are roughly mirror image, roughly is the keyword. Roughly the mirror image about the mean. But in this case, there are two lumps here, is symmetrical about the mean, but it is not moon shape. It's actually double moon shape. So it will fail the criteria. And if you predict 70%, you'll be quite wrong. Yeah, so that's roughly symmetrical but not roughly moon shape. You can also have roughly moon shape but not roughly symmetrical. So you can have roughly moon shape yeah, so it's quite moon shape here, quite a lump here in the middle, but not symmetrical because kind of like the right has a bit of more lumps and more meat, more area than the left. So it's no longer symmetrical and the prediction will be bad. So if you conclude that nine, up to 70% of people will earn between 90,000 to 110,000, you will be quite wrong. Okay, so that will be the case when empirical rule breaks down. So it has to be both roughly moon shaped and roughly symmetrical. Then you kind of get a bit of a free lunch. Why is that so? Well, because various factors and forces have already made the data roughly moon shaped and roughly symmetrical. And already, if you satisfy this, it's already quite similar to a normal bell curve already. So that's why empirical rule becomes quite predictive, quite accurate, even without measurements. Okay, so that's basically the reason. What happens if you cannot satisfy one or even both of these requirements? Then you can fall back on Chebyshev's rule because it is very generous. It can work with any shape and size of the data. Nice, right? It's very powerful, generally applicable. You don't need to satisfy any condition. So where's the catch? Well, the catch is it is not approximately equal to, it is at least, which is a very open-ended kind of result. So it's not very telling, it's not very accurate. It gives you some sense that, for example, at least 0%, if I tell you, oh, at least 0%, means some data will fall between 0 to 100. What am I telling you? It's like not much, right? Of course, there'll be someone, getting this falling into this range. So I'm not telling you too much when I'm being so generally applicable. And so that's the kind of long and short of Chebyshev's rule. So it it is nice. It can apply to any data, but it cannot tell you very precisely. So what's the result that Chebyshev's rule tells you? It says at least 1 minus 1 over k squared, all right, proportion of data lies within mu plus minus k times sigma, where k is 2 or more. 2 or more. So starting from 2, let's look at this a little bit. Mu minus 2 sigma to mu plus 2 sigma. What does Chebyshev's rule predict about the area, about the percentage of data within this segment? The area is going to be 1 minus 1 over 2 squared, which means to say 3/4, right? So 75% of data will fall within mu plus minus 2 sigma. So that's what Chebyshev's rule says, which is okay and not okay. If you can apply empirical's rule doesn't say at least. It says approximately. So it is like roughly equal rather than saying at least, which is open-ended, right? So that's nicer, more firm. But Chebyshev's rule just says at least. So we are, first of all, having to do with the greater equal to, and then this number is so low that it can be 80%, 85%, 90%, 95%, right? So it's like the predictability is way lower than if we can apply empirical rule. Let's try one more time. For k equals to 3, you can see that there will be mu plus minus 3 sigma. So how much of a data will be contained within, let me just choose the color, within mu plus minus 3 sigma, right? So over here, how much data is that? How much area is that? So according to Chebyshev's rule, k equals to 3, so that's 1 over 9. 1 minus 1 over 9, that's 8 over 9. Yeah, so 8 over 9, that's about 89%, yeah, of data, at least. So we're not sure whether it's 90%, 95%, 99%, 100%, not very sure. But from the looks of it, you can see that it's not too wrong, right? We almost have the entire weird shaped data embedded with just a little bit outside. So probably it's 96%, 97%, but we will never be sure. And Chebyshev takes a kind of a big cut, being very conservative, and says at least 89% will be there. Now, sometimes this is good enough, right? Because your population actually is not very large. 10 people. 10 people, at least 90% in there, it's like almost everyone, 9 persons or 10 people all in, right? So that's pretty good enough in certain cases. In other cases, this is too loose. We need something more accurate. For example, if it's medical kind of medical measurements where life and death is at stake, where money is at stake, and when investments and returns. No, so in certain cases, we might need to therefore actually go and spend money, time, and patience to sample and do more accurate measures. So again, with very little assumptions, very little work needed, why not, right? And this is a very nice result coming from doing nothing at all, doing no work at all, right? So that's nice. So just want to leave you with this understanding so that you may even begin to find some creative applications of these powerful tools.